Let's take a look at the case of a spring-driven oscillator where we have a small mass M, which is frictionless, attached to an ideal spring. It's pulled back to X max and released where it begins to oscillate. Recall from Hooke's law that the force from a spring is minus kx. So if we show that force, it's here. And the negative implies for a positive x displacement, we have a negative acting force, and for a negative x displacement, we have a positive acting force. So the negative here accounts for that. We can also apply Newton's second law. The sum of the forces in the x direction will be MAX. Combining these, we get negative kx is equal to MAX. We can write AX as the second derivative of the location of x, or x double dot. Rearranging this, we can divide by m and bring this to the other side, where we'll get the classic equation x double dot plus k on mx is equal to 0. And that is our classic equation for an oscillator. And notice that is a second order, ordinary differential equation. And there's a few ways that we can try to solve this. So we're going to solve for the motion. Now there's a few ways that we can solve this. Step one is to guess some function of x that satisfies that equation. And note that whatever that function is, x, whatever we pick, its second derivative has to take on the same form but be negative to it, so that when we add these, they cancel out to get us to 0. So we know that the sine and cosine function behave this way. So that's our guess. Let's see how we do that. So we're going to guess that x is some a constant times the cosine of omega t plus some b constant times the sine of omega t. And from there we'll take the derivative of our guess, which will be negative a omega sine omega t plus b omega cosine of omega t. And recognize that that's v. And x double dot will be negative a omega squared cosine of omega t minus b omega squared sine of omega t, and recognize that that really represents a. Now if we look at what we've got here, we have a function that looks identical almost to the one that we started with the exception that it's now negative. So let's check it. By plugging in these values here and see if it equals 0. So our check will have a, which is negative a omega squared cosine of omega t minus b omega squared sine of omega t plus k on m times x. which would be A cosine of omega t plus k on m b sine of omega t. And this has to equal 0, so we would call homogeneous equation. So what's required for this to work? Well, if we look, this term and this term will subtract out if omega squared is equal to k on m. They'll drop out, and this term with the other sine term would drop out with the same criteria. So that tells us that it's a valid solution if omega is the square root of k on m. Now that we've verified that this is valid for omega equal to the square root of k on m, which this thing is the natural angular frequency, and as such it should have units of 1 over seconds, which we can check. So the square root of k, which is newtons per meter, over mass, which is kilograms. And the square root of newton is a kilogram meter per second squared times 1 over meter times 1 over kilogram. If we bring the kilogram up, the meters go, the kilograms go, and we have the square root of 1 over seconds, which is indeed 1 over seconds. So that's another way of knowing that we have the right set of units here. A second way of knowing that is up here. That should be unitless. And we'd have omega t as 1 over seconds times seconds. So that's also working. So there's a few ways to check this. The next thing that we need to do is to figure out what these constants are, to find the constants a and b using the boundary conditions for the problem. So the boundary conditions in this case would be at x equal to x max, t was 0. We'll start the clock running here. Therefore, v would also be 0. That's where we released it at that point. So if we do that, plugging a 0 into here, we have the sine of 0 is 0, cosine of 0 is 1, and x at 0 is x max. So we'll find that a equals x max. And our second boundary condition would be that v is equal to 0 at t equal to 0. And this equation represents v, so cosine of 0 is 1, sine of 0 is 0, it takes that out, and this is 0. So we have that b omega is equal to 0. Therefore, b omega is equal to 0 in this case. Knowing that b is 0, it'll take out all of these portions of the solution. If we had started someplace else, let's say here in the middle, we would have found that these terms were 0 and these would survive. If we had started someplace arbitrarily in the center, both terms would have survived. So this is a classic solution for simple harmonic motion. We assume that it takes the form of a sine and a cosine. And in our case, our solution is that x is equal to x max cosine of the square root of k on m times from here, x dot and x double dot are also known by simply plugging in the appropriate values up here. And we find that they're all sinusoidal behaving as well. We'll find that harmonic oscillators of this type can often be related to a circle in terms of circular motion, UCM, uniform circular motion, or if we have some circle with some radius r, we'll have it rotating with some constant angular velocity. At any given moment, we can find the value for x here as x is equal to r cosine of theta, or in our case, r will be x max, and theta we get from the definition of omega as theta over time, so theta is omega t. So we find then that x is x max cosine of omega t over time. We can see that our value for x will oscillate in linear simple harmonic motion as the x component of the rotator spins around. So this is why we see the omega term showing up in this specific solution set for springs. They can be related directly to circular motion. If we take that one step further, we have a velocity v, which would be r omega, and if this is theta, that's theta, which makes this theta, and vx would be this component here, which would be v sine of theta, and it's in the negative direction, so vx would be negative r omega sine of omega t, in which case we again get the same solution from before, and we could take it one step further and solve this for the acceleration, which would be centripetal acceleration, which points here. And in the x direction, we would have r omega squared. Note again that this x component is negative, and since that's theta, this would be cosine of omega t1. All of these terms could have been derived from a unit circle that's rotating with some constant omega as well. Something else that's useful in this analogy is that if omega is theta over t, we can do this for one full revolution, where we'll get 2 pi radians over the period. And as such, we can solve for the period of one oscillation. So the period for one oscillation will be 2 pi over omega. But recall that omega is the square root of k on m. So this will be 2 pi on the square root of k on m, which will be 2 pi the square root of m on k. Notice here that as m goes up, the period goes up, not linearly, but it increases. That's more inertia. And the system is more sluggish in a sense. And as k goes up, the period goes down, and that's because the restoration force is larger. Also note that it's independent of x max. So this was one classic method using differential equations to solve for the harmonic equation. And anytime we see a plus in here in this form, second order differential equation without a central term, with a plus inside. We know that sine and cosine will generate the appropriate relationships for us. But it's not the only method. There's another method that we could have used, which we'll take a look at now, by separation of variables. Where we have x double dot plus k on m x is equal to 0. We can separate these, which will become x double dot is negative k on m x. And note here that x double dot would be defined as dx dot dt, which we can use the chain rule by multiplying and dividing by dx. And observe that dx dt is x dot. So this becomes x dot dx dot dx. And that dx right here is very useful because it can work with this x value over there. So if we take that and substitute it into here, we get x dot dx dot over dx is negative k on m x. We'll bring the dx up to this side, and these are both integratable now. This simply becomes x dot squared on 2, negative k on m, x squared on 2, plus some constant of integration. And this we'll get from our boundary conditions. And the boundary conditions, recall, were that at x equal to x max, x dot was 0 in our case. So this is 0. This becomes x max, and C1 is positive k on m x max squared on 2. If we plug those in and divide through by, and multiply through by 2, we find that x dot squared is k on m x max squared minus x squared. And we can take the square root of that. Now we can check that. Because it's really nothing more than conservation of energy. When we move the mass to x max, the energy in the spring at that point is 1/2 k x max squared, and the kinetic energy here is 0. When we release it, it'll be someplace here in the middle where the energy in the spring is 1/2 k x squared, where x is whatever distance we are away from there. And the kinetic energy will be 1/2 mv squared. And for a conservative system, we have no friction basically. We can say that this energy has to equal that energy. 1/2 k x squared plus 1/2 mv squared is equal to 1/2 k x max squared. Multiply through by 2. Divide through by m. And right here's what we're looking for. We get v squared is k on m x max squared minus this, which would be our x squared. So with that, we get the same solution. So really, this is just conservation of energy. It's interesting to note here that this is v as a function of x versus before we had v as a function of time. The two different ways that we could look at this spring system. So we could look at it as location-based, or we could look at it as a time-based function. It oscillates sinusoidally in time, and it follows this behavior in terms of its location in space. Our takeaway here is that we can solve this equation more than one way. We can solve it as time, where x is equal to some sine and cosine type fashion, and we can solve it as location by using separation of variables. Again, very good techniques for solving a very common scenario that we'll see with Newton's laws. Thanks for watching.